Right. Now we were discussing how to design simple logic circuits. And you can see we can do this for several ways. One, based on min terms, right? What do you mean by min terms? We can look at when the outcome is 1, we can write equivalent min terms. අපි එහෙම නේද කතා කරේ පොතේ min term එක අපි ලියලා මේක circuit එක ඇඳලාද එතකොට
circuit එක ඇඳලා min terms කියලා විතරයි
මම ඉවර කරලා නැහැ කියන්නේ මම මේවා කරේ නෑ නේ right okay so the last one I think I didn't put it here so let me put the last one we have a 4-bit prime number, right? We have we have 0, 1, 0, 1, 0, 1, 0, 1. Okay, we have to write down more, right? Have you done this? Finished this part?
yes
What a keyword? Oh, what's that keyword for that? Right, I will type by the way. So we have designed a logic circuit identify 4-bit prime number. So that means these are the prime numbers that I need to recognize. So which means, so this one becomes A dash, B, C, D. Then we have 1, 0, 0, 0, right? That is 8, it's 0. Then 1, we have 0, 0, 1. Yeah, that is also 0, 1. We have 0, right? We have 1, 0. That is 0. Then 1. We have 0. We have 1, 1. Okay, this is 11. That means we have 1, which means we have say A, B dash, C, D. Yes. Let me get your answer. Yeah, we have written like this. Right. Now the question is, since you have already sent it to me, we have 11, 13, and 17. That's correct. Right. Now we need to, design the circuit, meaning you can now use either Carnot maps So we have drawn the truth table, right? Now, yeah, since you have already finished, I will do this, until I type. I want you to obtain SOP, meaning we know that the SOP expression, yeah, write down. I will finish. Until that, you can start. Yeah, type what is SOP is, and then we know if type what it is, and then you need to simplify using Carnot, right? Can you do that for me until I will start from the beginning. Right. I want you to finish before me. So here is what we have: A dash, B dash, C, B dash plus A dash, B dash, C, D plus A dash, B, C dash, D plus A dash, B, C, D plus A, B dash, C, D plus A, B, C dash D. 1, 2, 3, 4. Oh yeah, we have 6 terms, right? Now we are supposed to draw the Carnot map. So now that we have, we can write down what we have here. Yeah. Can you send me, Kanta, the answer for this one? Okay, Bobby, what we did, we have completed the previous one. We were discussing designing a logic circuit to identify 4-bit prime number. So I think we have finished up to this point. So the outputs will be whenever we have, prime number, the output will be 1. So the outputs will be 1 when the value is 2, 3, 5, 7, 11, right? Then we have 30. That's what we have, right? So terms, we have 1, 2, 3, 4, 5, 6 terms are there. Okay. So what I did after completing this one, I have written SOP expression, right? Once I have the SOP expression, I'm using a Kano map.
Okay.
Right now, let's do it. Right now, if you look at this one, what we have is we have A dash B dash, right? A dash B dash means 0, 0. Then we have CD dash, right? This is 1. Yes. Then A dash B dash CD, this is 1. Then we have A dash B, C dash D, A dash B, C D, then A B dash, A B dash, C D, this is 1. Okay. The final one, A B C dash D, A B C dash D, A B C dash D. Okay. So here are the ones. Okay, simplify and send me the yeah. Yes, how many groups we are getting? I got the answer from Kant. Now let's group them. Remember, we try to find the group of 2, right? So that means 1, 2, 4, 8, and so on. So there's no 4 we can create using this. So we can create, groups of 2, right? Kanta, can you draw the circuit as well? So now to do this, now we can think like how to group them. Remember, when you're grouping, make sure that, now for example, in this one, we can combine these 2. Yes. Then, yeah, you can have these 2 and these 2, but since with these 2, this is covered, you don't have to convert these 2, so there's no point. Then we can combine these 2. And for this one, we have to connect with whatever we have here. Right. Now let's write down. So what is we are getting from here? We have A dash, we have B dash, then this one will be C. Yes. And here we have A dash B, then we have D, then if you take these 2, that is CD, from here we will get B dash, so it should be B dash CD, right? And the final one, this one, yes. What we have here is, we'll get B, then we have C dash T, right? So now once you simplify this, now we can get the equation, right? Now the simplified equation we can write down, that is F equals right, we can say F equals A dash or A bar B dash C plus A dash B D plus B dash C D plus, right, B C dash D, right? That's what we have, right? Now I want you to draw the circle. So the logic circuit for the simplified one. Right. I'm going to use logically here for the easiness. Yeah. Now for that, I'm going to show a couple of things, right? Yes, we will have 4 switches to indicate the inputs. Okay, so that part done. Yeah, this is to say that, okay, we have A, then we have B, we have C, we have D. You can draw, right? We have B, we have C, we have D, right? So these are the 4 switches. Now, yeah, we need for everything, we need NOT gate as well. So let me put some NOT gates, right? There are 4 NOT gates I'm going to have. Yeah. So get each individual one. Then we have, okay, in this one is a sum of products. So the product is the main one. So we need some AND gates. And remember what we need is we have to have 3, right? AND gates. So I'll be using right. Let's copy, paste. Right. Right. Now we need 4. So that I put it like this. Right. Finally, I need O gate. AND gates are okay. So one single O gate. But this time we need to have like 4 inputs. And then to represent the output, I have bulb. Right. So let's connect the wires. So we have this. Right there. The next one will circuit A dash B dash C. So we have A dash, we have B dash, then we have to have C. Yes, then one A dash, B D, we have to have B, then we have to have D. Yes, third one B dash, we have to have B dash, C D, C and D. Next one B. So we have to have B, then C dash, then we have to have C dash, right? Then we have to have D. Right. So one NOT group is not required. So I have removed D dash is not there. So A dash, B dash, C dash is there. Right. This is the circuit. Right. Can I have your attention now? Let's see. Now this represents 0, 0, 0, 0. It's not a prime number. But whenever we have, let's say, 0, 0, 0, 1, let me see, this is as 1, Yes, again, bulb is off. But whenever we have 0, 0, 1, 0, you can see bulb is on. So that's a prime number, right? Then 3, that is also prime number. 4, that is not a prime number, but 5 is a prime number. 6 is not a prime number. 7 is a prime number. 8 is not a prime number. 9 is not a prime number. 10 is not a prime number, but 11 is a prime number. 12 is not a prime number, but 13 is a prime number. 14, not a prime number. 15, sorry, that is 13. 15, it's not a prime number. Right. I hope you understand what happens here. So now, yeah, you can complete by drawing that. And you can send it to me actually. So you can see some circuit drawings just to elaborate what we are trying to do here. So 2 is a prime number. You can see that I put some just to elaborate some of the positions. Maybe then I can have 13. Yeah, that's a right number. I think this is enough, right? Okay, so now that we have drawn the circuit, yeah, so the actual one is, you know that we have to get ICs to build this one. So that part I'm not going to do, but yeah, so in actual case, that is exactly what we have to do. Right. Okay. So finished. A couple of homeworks. The first one, there's a lamp outside, and then the lamp should work when it is dark and somebody actually comes towards the door. So first thing is you have to model this and draw the truth table. Sometimes you don't need to simplify if it is a very simple one, but if it is a complex one, then simplify. You can use either Boolean algebra or Karnaugh maps. Then I want you to draw the circuit. Right. So those are some homeworks, right? And I will send you more when we talk about this sum of products and also like product of sums. Then I will give you more exercises on this. Right. The next thing that we are going to do, right? We are going to look at these logic circuits now we have done. We are going to look at these combination logic circuits used in CPU and in sequential circuits, right? So we are going to look at, some major building blocks and truth tables for different circuits, and then something called flip-flops, right? So that's what we are going to do, right? So, so let's start. It's a new topic, subtopic actually. So let's write down the we can talk about first, okay, combinational circuits used in CPU, right? That's what I'm going to do. Okay, combinational logic circuits used in CPU. Now there are many combinational circuits are used, right? Right. So under that, what I'm going to look at is what is inside, and then we are going to look at how we can use this, right? Now, the first of all, we'll write down what combinational circuit is, right? So we'll start with that one. So combinational circuit means we can say combinational circuit transforms a set of inputs to a set of outputs, and that's all, because you will see the difference in the other ones. Okay, so that means so let's say we want to have combinational circuit. Right. So what we have here is combinational circuits. This is the, let's say, combination circuit, right? So in combinational circuit, this is what we have. And what we have is inputs, right? We have a bunch of inputs. We have a bunch of inputs. Right? So you will have a set of inputs to this circuit. Yeah. And then you will have a set of outputs as well. Right? There'll be a set of output as well. So we can have, I'm going to say present. The term present means you will realize we can say present inputs. The reason why I have put present here is sometimes we in circuits in the other type we will discuss, we can use previous states as well. Okay, so this one is, we call it present output. Right. Right, now let's write down some features of combinational circuits. Yes, these are the points that we need to discuss. We can say every output will be a function of inputs, right? There's a reason why I have put like this. So that means the output is always depend on the input. That's what I want to say. For the given same in, the output will also be the same. The circuit consists of AND gates, OR gates, exclusively OR gates, or we can NOT gates, and so on. So that means these are the ones we can use. There is no memory because we are going to discuss memory. Right. So these are the things we should know before we proceed. So in this one, what we did, we use half adder. In half adder, what we know is it simply performs simple addition. And if you take single bit additions, if you have 0, 0, we'll get 0, 0, 1, it's 1, 1, 0 is 1, 1, 1 is 1, 0. So we need to use at least 2 bits. So the one bit we known as a sum, and the other one is carry because it goes to the next place, next location. So the inputs are A, B. We output, we can say sum and carry. So when you have 0, 0, sum is 0, and there's no carry. 0, 1, sum is 0, and there's no carry. When you have 1, 0, yes, it's 1, there's no carry. But when you have 1 and 1, the sum is 0, and 1 will be carried to the other position. Now, with that, we can write two expressions, some expressions. We have to consider these two ones, that is A dash B plus AB dash. From the explosive OR gate, we know that this means A XOB. Similarly, carry, we have only one output, so that equals to A dot B. And to do what I did is I actually draw the circuit, and this is representing the half adder. Now, the second one, right? So this is combinational circuit. I told you this represent the combination circuit. So if I compare what we have done earlier, right? What you will see here is Right. Now, this is combination circuit, but what we have is half adder. We have hard adder circuits. The inputs are the 2 bits, right? So what we had is we have A and B. So those are the 2 inputs we had. And then what we got as the output is sum and carry. So the previous one we are getting here sum, right? And here we are getting, right? So you can see it basically mapped the input to the output. Right. Now let's look at the next circuit. That is what we call full adder. Now, what do you mean by full adder here? Right? You can look for adding 3 bits. Right? So in full adder, yes, right? Now we are going to look at now adding 3 bits for the full adder. Right? So then now adding 3 bits here means we know when we are adding binary numbers. So let me put it this way. Right? If you have something to add a binary number, we know, let's say 10101111. So we know that we are adding these 2 bits, 0 plus 1, that is 1. Adding some 2 binary numbers. So in this particular case, if I add 0, 1, it becomes 1. So this is binary addition. Right? Then when you say 1 and 1, what will happen? 1 and 1, we will have 0, and there will be a carry bit. Right? So there will be a carry bit. So in this one, you are getting a carry here, 1, 0, 1. So again, this is 0. There will be a carry bit from here, 1 and 1. This is 0, and then we have 1. Right? So now when you look at some 2-bit addition, actually you will have a 3rd bit also coming from the previous state, isn't it? Right? So because of that, right, I'm going to discuss how 3 bits could be added. That means the input will carry from previous carry. So whatever comes in, I'm going to say carry in. Then I'm going to say carry out. Right? So for that, let's draw a truth table, right? So we can say, okay, truth table for full ladder. We have A, we have B, we have C. That means I'm going to say this is carry in. I'm going to say C in, right? Carry in. And then outcomes are, we have some, I'm going to say carry out, right? Just to say what will be the answer. So that means the first three are the inputs, right? And here we have outputs. So let's put up the values now. 3 bits, meaning you know how to put it. Right. Now for the summation, we know when we add 0, 0, we'll get 3 zeros. Sum will be 0, right? The carry out will be also 0. So when you have 1, the sum is 1, right? And then there's no carry out, that is 0. Then sum again 1, carry out will be 0. When you have 1, 1, right? When you have 1, 1, we will have the addition. Sum is 0. Yes, this is 1. The next one we have sum is again 1, and there's no carry. And here we have 1 and 1. So that means in this time, what happens? We have 0, the sum is 0. Then there's a carry 1, and 1, 1 again the same. So this is 0, carry will be 1. And when you have this, yes, sum will be 1. Yes, carry out will be 1. Right, so that's what we have. Now, I'm going to finish this one. I want you to come up with the expression for sum and carry. Can you do that? right? Write the expression for, yes. Right. Now that we have done this, let's see how to write expression for this. Right. Now let's write the sum expression. So if you draw the look at the sum expression, let me use both Karnaugh maps and Boolean simplification. Right. So we were looking at the sum expression. Sum expression means you have to look at these ones. So I can write down the expression first. So sum, I can say I have this one. So what is this one? It's A dash B dash C in A dash B dash C in plus we have A dash B C in dash plus third A is A B dash C in dash plus 1, 2, 3, 4, right? Last one A B C. Okay, this is what I have. Right. If I try to draw this, we know what is A dash. So let me take different color. Yeah. So what we have is A dash, B dash C, right? B dash C, that is, this is one. Then A dash, B C dash, B C dash, this is one, right? And then when you say A, we have B dash, C dash. This is one and this is one. If you look carefully, this representation, this is exclusively O. XO pattern is here. If you're not really sure, you can try, Boolean simplification. So let me do that for you. In Boolean simplification, we know, right? I will take a copy of this and try to simplify. Right? Sorry, I think I missed something. Yeah. Right. Now you can see what are the common values. So in this one, for example, you can see, okay, one thing is missing here. It should be C in. Sorry. Yes. What are you going to do? Huh? We have C in. Simply we also we have to have C in. Right. Okay. Now you can see the common ones. Particularly, I would like to get C in and C in dash. So for example, I'm first one, I'm getting C in. So from A's first statement, we will get A dash B dash plus. So here also Cn, we will get AB, right? Plus, then we have C in dash, we have A dash B plus A B dash. Now, if you look carefully what we are getting here, we can say that this is same as C in A dash exclusive B dash plus this is C in dash, we have exclusive O B, which means to simplify all these things, this is finally equivalent to, we will get C in exclusively O, A exclusively O, then B, right? So this is a sum expression. Okay, now that we have done some expression, this is a bit difficult, so that's what I did. Okay, I want you to do the right see out expression. Right, that's a homework. So with that one, we'll finish for today's session. Tomorrow, 5 o'clock, I will take the normal session.